Okay. Last time we considered a general quantum field theory. It's a gauge theory having fields phi 1 to phi n, and we assume that this theory has an action S phi, classical action S phi, S0 phi, and then we studied what are the most general possible transformation of fields that keep the action invariant, and then we studied what is the most general possible algebra that it can have. So we studied the most general possible gauge algebra that we can have, and then we found that the gauge algebra is an open algebra. So let me just write what is that. So let's consider transformation delta phi I given by the action of a generator Ri alpha acts on phi I with gauge parameter, say epsilon alpha. So let me write it this way. Yeah, depends on position x. So this was the transformation, and then we studied its algebra, and the algebra is given by delta 1, where you assume that the parameter is epsilon 1. So you can compute the commutator, and then its action on field phi I is given by the most general structure that we found was that it's a sum of a gauge transformation plus a trivial gauge transformation with the so-called structure constant. Plus a term that is proportional to the equation of motion, and then we said that we can study the higher identities that satisfied by this transformation. Basically, we analyze we can look into the Jacobian identity, and then that will introduce relations between T and this is not epsilon, this is E. The tensor that we introduce E, so all this tensor will satisfy further conditions, and then when you try to solve that condition, you have to introduce further tensor structures, and all those structures tell you about the structure of the gauge group. So these are those were the gauge structure functions. So we see that the general transformation is characterized by a number of gauge structure functions, and these gauge structure functions satisfy a lot of identities or many relations between them. Then we found that, or we felt that if you start assuming that this gauge theory has a further structure, that means the gauge invariance, if it is further reducible to lower gauge invariances, then the algebra becomes more complicated. Basically, you have the same algebra, but its solutions start having more complicated form. That means you will have more number of structure functions, and these structure functions will again have certain relations. So the situation becomes so complicated, and why we should be really careful about such a theory, because we want to identify what are the dynamical degrees of freedom, and we want to study a quantum field theory for those physical degrees of freedom. So it's important to take care of the gauge structure. Now, the simple gauge structure, if you don't have such a general gauge structure, let's say we don't have terms proportional to the equation of motion, or if you have a situation where the commutator of two non-trivial gauge transformation won't produce such a term, such a trivial gauge transformation, then we could use the simple Faraday-Popov quantization method. Now, once you start seeing a lot of complicated structure or more general gauge structure, then it's not convenient to use Faraday-Popov quantization. It's not just convenient, you won't be able to do it. So what we hope was that if we could characterize or bury all the structure functions into a single function, say some function S.
Is it not possible to introduce some auxiliary fields and try to close also?
Yeah, that's what so that's the basic idea. So what you have to do is you can introduce a number of auxiliary fields, and then one can hope that you have fields plus auxiliary fields, and then you can write down an action for this combined system, and then hope that the action will contain all these structure functions, and the action that you constructed using all these auxiliary fields may satisfy some identity, some equation, which is not just the classical equation of motion for the action, maybe some further identity, and that equation may contain all the information about the relations between these structure functions. That was the ideal situation that we are hoping for. And then the claim is that PV quantization basically does that. So we would like to discuss a classical PV quantization in the first section, and then we will discuss how to quantize the theory. So this is the classical field and field formalism. Since this was mostly studied by Battalion and Wilkowski, this is also known as BV formalism. So BV formalism can be stated as a number of steps, or basically I can give you a recipe. So the recipe is as follows. So let's start with gauge theory having gauge field phi 1 to phi n, and then assume that the action is S0 phi, and on the top of it we assume that the gauge structure is such that it is an nth stage reducible gauge theory. That means if you start with this configuration, then you realize that you have such a transformation that keeps the action invariant. Then you realize that this transformation itself has a gauge invariance. So that's the first stage gauge invariance, and then the first stage gauge invariance may also have some further gauge invariance. So you go down up to the L stage, and then you don't have any further gauge transformation that keep the L stage gauge invariance. So the these are matter fields or gauge field, whatever that you have in the theory. Yeah, so there is no ghost field in original set. You don't have any ghost field here. And to introduce the ghost field, first you have to understand the gauge structure. That depends on what kind of action that you choose, right? So once you realize that your theory is L stage reducible, which you can anyway find from your action, your classical action, and then you have to introduce ghost for the first gauge transformation, and then a ghost for the ghost. Basically, you have second gauge, the first stage gauge invariance has a gauge parameter. Corresponding to that gauge parameter, you have to introduce a set of auxiliary fields. Then you go down till you reach the L stage. That means it's not one set of ghost field that you have. So you have a number of ghost fields. So that's the first step. So let me write down the different steps. So the step 1 is to introduce or identify what is the field content of your theory. Basically, you have to identify the gauge structure and then introduce a notation capital phi a, and this corresponds to a collection of fields. The first, the fields of the kind phi I, then the set of all ghost field that you have to introduce for the gauge invariances. So this is C alpha S S, and S run from 0 to L, and alpha S runs from 1 to M1 to MS. So here M1 corresponds to the number of independent gauge transformation, or number of different gauge transformation that you can have. And M1 of, so let's say at the 0th stage you have say M0 number of gauge transformation, and then all of these M0 gauge transformations may not be independent. So I'm just saying that these are number of gauge transformation, they may not be independent. So this is the first step. Introduce a field and the corresponding all gauge fields. So once you have done that, so you have to do it for all phi i's. So A is the index corresponds to phi 1 to phi n. So now you have to assign a ghost number for these fields. So it's a number that you associate with all fields. The ghost number for field phi I is 0, and the ghost number for say C alpha 0, 0, the first stage gauge transformation, the gauge field corresponding to the gauge invariance for the first at the first level, that has ghost number 1, like you see in Fadi-Popov, and then you can continue, and then you have a S stage ghost that has ghost number S plus 1. So this is the way one should assign ghost number for all the fields. Then you have to tell what is the parity of each field and the ghost fields. And parity I denote by epsilon. So this is different notation. The parity of C alpha S is given by the parity of the gauge parameter at S stage plus S plus 1. And then since it's parity, you have to just take the mode of 2. So that's the first stage. You identify fields, ghost fields, assign ghost number, then find out the parity. So that's the first step. Now the second step is not familiar from Fadi-Popov, and the second step is to introduce antifields. So here you introduce an antifield for each field. It's a new step. So this is the kind of auxiliary fields that you have to introduce for reproducing the gauge structure or closing the algebra. So here, for each field phi I, we introduce an antifield which I denote by phi star A. Here A runs from 1 to n. So for all these different sets, we have to introduce a antifield. So if you have phi I, small phi I have phi star I, and for C alpha S, I have C star alpha S. So for every single field, you have one more field. So you are basically doubling the number of fields that you have. And you can think of these antifields in some sense as a BRST BRST transformation coefficient sources. So we discussed BRST transformation in the first lecture, and then we said that it's interesting to introduce a source for each BRST transformation. And antifield can be, in some sense, identified with these sources that you introduce there. And again, you can define ghost number for each antifield. So here, it's this is a part that is new in BB formalism, and you have to do the assignment in a particular way to recreate all the gauge structure that you have. So the assignment of ghost number and the parity is as follows. The ghost number of field of antifield phi star A, this is a capital, this should be equal to minus of ghost number of field phi A minus 1. So this is the condition that the ghost number for the antifield has to satisfy. Then the parity is exactly opposite of the parity of field phi A. So this is the second step. Now we introduce an anti-field. So at the end, when you do the calculations, you have to throw away these anti-fields by using an appropriate gauge fixing. So that I will discuss later. Now we have to introduce the notion of Ante Brackets. So I'm setting the stage for writing down the equation that reproduces all the relations between different gauge structure functions. So for that, I have to introduce certain notations. So the most important notation is the Ante Bracket. Say you have a function x. This is a function of field and anti-field, and then another function y, which is again it's a functional of field and anti-field. So I'm going to define an anti-commutator or anti-bracket that's given by the right derivative of x with respect to field phi A and the left derivative of y with respect to phi A star minus right derivative of x with respect to anti-field phi A star and left derivative of y with respect to field phi A. So this is the definition of an anti-bracket. Now what do I mean by right derivative and left derivative? So let's say I have a functional of field and anti-field f, and then I can consider a small variation of f under a variation delta phi. And then with respect to right derivative, I can write this variation as del r phi with respect to the field phi I del phi I. This is the right derivative. And the left derivative gives del phi I into del L f del phi. When the field phi is bosonic, it won't make any difference. But if you have a fermionic field, then whether you define right derivative or left derivative, that matters. So you can easily find that the relation between left and right derivative is given as follows. Just a difference in sign. So right derivative is related to the left derivative with a sign factor. That depends on the parity of x and parity of phi. Now this,
Yes, when x equal to y, the bracket will give you 0.
depending on whether it's fermion or boson. If it is fermion, both x and y, if they are fermion, this is equal to 0. There's a trivial identity. Now if it's a boson, then it's not equal to 0, but it's just 2 of this factor. So if for bosonic field, if it is equal to 0, then it makes no sense to introduce anti-bracket, because at the end I am going to use this definition or this notation for writing an equation for field for the action, and action is a bosonic object.
Will there be, so will there be something like a Jacobi identity for this kind of a thing, or?
Yeah, you can. Yeah, I'm going to write down the identities. So you can think of this as a Poisson bracket, almost like a Poisson bracket.
That's what I was thinking, like, but if x equal to y, then it is not.
Though it's more like a graded version of Poisson bracket. So the point is that
Graded version usually shifts the sign, right? I mean, whether it's minus or plus.
yeah. So even in Jacobi identities, those signs will appear. That's the only difference. So the point is that anti-brackets will satisfy certain identities.
Definition, the sign is always minus.
Yeah, definition sign is always minus. And so the point is that it's, like I said, it's more like a Poisson bracket for the Hamiltonian. So in Hamiltonian formulation, you have the Poisson bracket, and the corresponding thing in the Lagrangian formulation is anti-bracket. So we saw this thing coming even when we discuss ingestion equation. And in fact, we can derive ingestion equation directly from BB formalism. So let's say you have the definition of anti-bracket given this way. Then if I change x and y, so let's consider the anti-bracket of yx, then that's related to the anti-bracket of with anti-bracket of xy in this way. It's again a sign difference. And then it satisfies identities, Jacobi-like identities. So you have xy, anti-bracket of xy, which is again inserted in another anti-bracket. So you have anti-bracket of xy, then anti-bracket with z. What is? Oh, this by epsilon. So this is not the gauge parameter, this is the parity. It tells you what is the Grassmann-Ality of field phi. Plus a sign factor epsilon x1 x is equal to 0. And you can check the Gauss number for anti-bracket. Gauss number of anti-bracket of xy is given by epsilon, Gauss number of x plus Gauss number of y plus 1. And statistics or the Grassmann-Ality of xy is given by Grassmann-Ality of x, Grassmann-Ality of y plus 1. So the point is that the anti-bracket itself has a Gauss number, and it has a Grassmann-Ality. So given that, one can check what happens, like Kalyan was saying, what happens if x equal to y equal to b, where b is a bosonic function. Then it's easy to check that anti-bracket of bb is given by 2 del r b, right derivative of b with respect to phi a, and left derivative of b with respect to anti-field phi star a. And assume that x equal to y equal to some fermionic field, say f, then anti-bracket of f with f itself is equal to 0. So this is a trivial statement. So for that we have to use this relation. Zero. It's a Grassmann even.
So if you take the very first equation,
yeah.
then like on the, so y comma x should be equal to, let us assume that both y and x are boson.
Yeah.
Then that should be equal to minus of x comma y.
See, so you're saying, say,
Let's say both x and y
yeah,
are boson, right?
yeah.
So then
Maybe I think that's a minus. Yeah. So now we have enough things to define what you mean by a mass traction. So I can make mistakes. Kalyan will correct. So we have. I'm going to introduce
it's a bit unusual, right? Like introducing a bracket where like when the things are equal, it is still not zero. All the Poisson brackets, commutator, etc. are usually are anti-commutators.
The point is that, so here, field and anti-field have opposite statistics. That's the main reason why you have that. So I'm going to introduce a classical master equation. This is the most important thing for classical BV formalism, and that's a stepping thing for the quantization of gauge theory. So consider, so we said that we doubled the number of fields in our theory. So we started with fields phi I and then introduced all the gauge field, then defined that as a set of fields. So the field in BV formalism means the actual fields in the theory plus all the gauge fields, or all the auxiliary fields that you have to introduce. Now,
one question, by introducing this doubling this set of fields,
yeah.
Which presumes like introducing equal number of the auxiliary fields. Is that right?
I mean, it's an auxiliary field with some certain particular kind of gauge numbers, and
That's fine.
yeah.
But the number of
It's exactly equal.
It's
Exactly equal. So that's a main condition. So it seems like, okay, you double the degrees.
Or the numbers need not be related, or maybe like sometimes you might get lucky and you need to get away with.
No. So you have to have enough equal number of anti-fields.
So then like it will close, everything will close.
It's not closing. It's the basic thing is that you have the same algebra, but the point is that you can encode all the information in a single equation, or in a single function and in single equation. So that's like, I mean, the starting of Lord of the Rings. So
will it lead to open algebra the way you defined, or will it lead to so-called closed algebra?
no, it will give you open algebra, and I will derive open algebra for string field theory. So this is the classical master action. So let me, so for this we have to introduce a classical action in BV formalism, basically the classical master action. So this is just a functional of field, all fields and anti-fields, satisfying a certain condition for gauge number. The gauge number should be equal to 0 for this. So I am keep on introducing some same S because it's again an action for field and anti-field. And the statistics of or the Grassmannality of S should be even. So it should be 0 mod 2. And the gauge number of S should be 0. And so this is the first thing that you have to do for finding classical master equation. You have to introduce a functional of field and anti-field having this satisfying this condition. Once you have that, and on the top of it, so let's say, let me introduce another notation, CA. So CA denotes all fields and anti-fields. So a particular C1 may denote a field, and Cn plus 1 denotes a, and so A runs from 1 to 2n. So half of CA denotes fields and half of them denotes anti-fields. So in terms of this variable, you can write down the equation of motion for this action. And that's given by right derivative of S with respect to CA. This is equal to 0. This is the equation of motion, classical equation of motion for field and anti-fields. Now we are not going to analyze this equation. So what we are going to analyze is the master equation. So what is classical master equation? The classical master equation is an equation on the top of classical equation that you have. So the equation is the following. So take the anti-bracket of S with S and demand that that's equal to 0. So this is the classical master equation.
So when you say it's on top of the equation of motion, what do you mean by among this and in addition to that?
So if you, anyway, when you're looking into the classical regime, you want to have a classical equation. So this is a classical equation, and this one, so this is an equation of motion, and this one is not actually an equation of motion. This is basically an equation for the gauge structure.
So like one asked last time. So this is like this Euler-Lagrange.
Yeah.
You assume that you.
Yeah. So.
All ETs.
Right. So the point is that when you do this variation, I mean you generate all the generalized Lagrangian, Euler-Lagrangian equations, because you don't know your action. See, your action might have so many derivatives and all the stuff. So the form of action may not be just Euler-Lagrangian. I mean Euler equation that you usually see, because it's complicated. Yeah, exactly. So you just do the variation, maybe using left or right derivative. So here, basically, see this. How come you got right derivative? So we just utilize this equation, right? So you do a functional variation, and then get all the equation. And Ante Bracket, using Ante Bracket, you impose one more condition. See, we can impose this because we double the number of degrees of freedoms or the number of fields that you have in your theory, and so you use that, and then you demand a equation, and then now we are going to study what are the consequences. Now this equation, using this equation, so what you are going to do is the following. So we demand that the functional that we introduce is going to satisfy this equation. And you can have several solutions, and all solutions are not so interesting for us. So, and I will tell you what precisely the condition that a solution should satisfy in order to make any physical sense. So let us start with this equation. So just reminding you that this is a differential equation in the space of field and antifield. So this is given by right derivative of s with respect to phi a, and then left derivative of s with respect to antifield phi star a is equal to 0. So you can see that this is a differential equation that you write down in the space of fields and antifield. Now you can check that when you do a following transformation. So basically I'm going to analyze the gauge invariance of action, or this generalized action, master action. So you can consider the field CA and then do the following transformation: CA going to CA plus RAB CB, where RAB is a matrix that you construct using your BV, using your master action. So RAB is given by some matrix theta AC, left derivative with respect to CC, and then right derivative with respect to CB, and it's acting on the actions S. So this is a transformation that you can perform on the fields or antifields, and then one can easily check that if we plug this into the equation or into the action is invariant, because del R, right derivative of S with respect to CA multiplied with RAB is equal to 0 due to the master equation. So that means when you do a following this transformation, your master action is invariant. So you should remember that. What is master action? Master action is a functional that satisfies this differential equation. So one can use that differential equation to show that such a transformation, this kind of a transformation will keep the action invariant. So that you can think of as the gauge invariance for the master action. Oh, so I didn't write it. So this is a symplectic matrix. Theta AC is given by, or AB is given by the matrix delta AB minus delta AB. These are the metrics that you see in symplectic geometry. Yeah, they can be different. Yeah, but you have an equation that's defined without referring to a statistics, right? So you're just using this equation. So this is your gauge invariance. Now we have to see how many number of independent gauge invariants are there. So you can do a gauge invariance for this transformation for 2n number of fields, right? So it looks like you have 2n number of gauge transformation. If that is true, then that will just throw away all the fields and anti-fields that you have. So that's not a sensible thing to do. So what you have to do is you have to check what is the rank of this matrix RAB. That will tell you how many independent number of transformations are there here. So to do that, one can do a simple exercise and check that RCA, RAB, and assume this on-shell condition for both fields and anti-fields. When you do this multiplication, it's basically just taking the square of matrix R, and this vanishes. So you have RAB, or you identified that this matrix is nilpotent on-shell. Now, if you study the matrix analysis for such matrices, or this matrix theory says that when you have such a nilpotent matrix, then the rank of such a matrix. Is this action itself?
Or is this second derivative?
Oh, yeah, it's a second derivative, right? Yeah, it's a second derivative.
So if you multiply that by del RS over del ZA, you're saying that.
Yeah, so it's basically a total derivative of mass traction, this mass BV equation.
So just to clarify, do the BLs and BRs commute or?
So you can again use this relation. Right. So you can derive this fact that these matrices on general basis, you can derive that this is a nilpotent matrix, and such nilpotent matrix have rank less than or equal to half of its dimension. So the rank should be less than or equal to n. So this is a thing that you can derive in general. So that means you can have a theory, or you can have a particular solution having the following property. So the matrix RAB that you compute using that particular solution, you can demand that has rank R equal to n. So assume that you find a solution for BV equation such that when you compute this matrix, that matrix has rank equal to n. Then that solutions are the one which are more interesting for us. So why that is interesting? That is interesting because you will see that if rank of this matrix is equal to n, that means you have n number of independent gauge transformation. You can use those n number of independent gauge transformation to throw away all the anti-fields. And that's what you expect, right? You don't want your anti-fields in final computations, right? So if you want to compute S matrix elements, you don't want to see them in the final answer. You don't want to use anti-fields in the final step. So you can have solutions that have that has the property that at the end you won't be able to throw away all the anti-fields. So you don't want that solution. So all those solutions satisfying this condition that R equal to n are known as proper solutions. So they are the solutions of our interest.
It's not the regular gauge invariance.
Huh?
But you still have the regular gauge invariance.
Yeah.
So these are the physical degrees of freedom yet.
So these are not the physical degrees of freedom. Only after you use the proper solution, then you can throw away all these unphysical anti-fields. And even after throwing it, you have further gauge invariance. Right. because anyway you have all this ghost field hanging here. So you will see that even after gauge fixing, you have BRST transformations, BRST invariance. So once you do the gauge fixing, then you are fine. You can define a consistent path integral. So
there is a guarantee that you will be able to find a solution for which the rank equal to n.
yeah, so that is something which is guaranteed. So this is something this has a rigorous proof. So given that, so I haven't finished it. So the point is that so if the solution has this property, then that's interesting. Now on the top of it, when you set S phi with all the anti-field equal to 0, then this should be equal to the classical action. So this is a boundary condition for the solution. So if you are constructing a proper solution satisfying this boundary condition, then it is guaranteed that such a solution exists. So this is something people can prove using all this homotopy theory. So this is guaranteed. You are guaranteed to get a classical master action, and you are guaranteed to get a classical master equation. So basically you can get the proper solution for the master equation.
So presumably that the condition means that there can be solutions for which the rank is less than
less than it, right?
And as you said, if the rank is less than n, you won't be able to get rid of
all the anti-fields.
But nevertheless, mathematics can still go ahead and
Yeah, maybe you can study it, but I don't know whether people have studied. So this itself will give me a feeling that, okay, why should I study them? Maybe that it has some interest, but I don't know. Usually, you look for physically sensible theories that are the ones which are producing consistent mathematical things.
Actually, something like the resulting equations do have some solutions with the rank less than n.
Yeah.
But still be interested to see what is.
Yeah, one can study. Yeah, but I don't know what is the meaning of it. So I won't then that moment when I decide to do.
Solutions do are there, is it?
Yeah, there should be. I don't know whether people have studied it. I am not aware of any situation where someone go that crazy and then study. It's allowed. It's allowed. It's allowed.
Allowed is, as you said, the theorem says that the rank has to be less than or equal to
Yeah.
n. Then the question is whether the solution
Whether it's
will presumably depend on the action.
action, right. So far I haven't assumed any dynamics for this theory, and then usually we study familiar examples, right? And in familiar examples, it works. So you can quantize using electrodynamics using this one. I mean, anything that is already quantized can be done in this way.
So that means that there won't be solutions with a rank less than n.
I mean, it might be because if you are looking into that kind of solutions, then anyway that won't corresponds to any known your sensible physical theories, right?
No, that is fine. I mean, that you explained.
Right.
The question is, will such solutions still be there even for
It might be. I don't know. I haven't even studied them. And maybe it's also interesting to check what happens in those kind of theories. I mean, where it goes wrong. I mean, what kind of physical principles are getting violated, or is it that there is another mechanism which allow you to throw away all the degrees of freedom? I mean, all these anti-fields. I don't know.
So there is no such solution that is known yet.
I don't know. Maybe there exists, but I don't know. I'm not that familiar with that kind of questions. Now, what one can do is
These anti-fields don't really have any physical meaning, at least the way.
yeah, they don't have any physical meaning so far, I think.
So, but on the other hand, once you introduce and do the mathematics, it's okay. There is mathematics.
Yeah.
And if for such a solution is there, where you will not be able to get rid of anti-fields, it is something totally different theory.
Yeah, it might be something totally different. But at least that's not a first step to quantize your theory with which you started.
That comes next.
Right.
It will mean that it's a theory in which there is a background which can create this anti-fields.
Possible, yeah. So, but the anti-fields themselves are supposed to be unphysical.
Yeah, so it will be correspond to a completely different theory with different degrees of freedom.
No, I think the point is that here one should remember that we start with a specific classical theory. Now what we are doing is we are setting up the stage for quantization. So the sensible thing to ask is whether this is the correct step to start doing the quantization. If you choose non-proper solutions, that's not the correct step to start quantizing your theory. So anti-field itself won't have any meaning to start with, because you start with a classical system, and that classical system have no way to know about anti-fields.
Yeah, it's like in path integral when you turn on the classical sources.
Right.
That's just a trick to use it to pull down different fields in position function. At the end of the calculation, you always set the classical sources to zero.
Right.
These are like anti-fields are basically classical sources for this.
I mean, when you have BRST quantization, like see, remember that there are situations where when BRST quantization won't work.
Exactly. So I'm saying that if you don't, at the end of the day, to reach a situation where you cannot set some of the classical terms corresponding to this equals to zero, that's basically corresponds to a different theory than the one you started on.
Yeah, so that's true. So that's not the correct step to start with. So the point is that now once you have all this thing, so you can start. So now you know that you have a classical master action and that satisfies master equation. Then it has certain gauge invariance. Now you can expand the classical action or classical master action, and then so how you expand? You expand with respect to the anti-fields. So you start with S5 and then start expanding it. So the expansion has the initial term as classical action for the original classical theory, and then you have all the remaining terms. And all the remaining terms will reproduce all the gauge structure functions. So you will start seeing gauge structure functions when you expand it. And you are able to do that because all the fields and anti-fields have certain parity and certain Gauss numbers, and then you want that the total Gauss number for each term should be equal to 0. So that condition will reproduce all the gauge functions, all the gauge structure functions, and then once you take this expansion for the classical master action and then put it into the classical master equation, then this will reproduce all the relations between all the different gauge structure functions. So the expansion of master action contains all the gauge structure functions, and the Ante bracket of action with action itself will reproduce all the gauge structure relations that you have. So if you want to check it, you can take the first reducible gauge theory that we discussed last time and then derive independently all the gauge structure functions, or at least some of the initial gauge structure functions, and then find its relation between each other. That's something which you can do as an algebraic exercise, and then you can check whether expanding same thing using classical master or whether you are reproducing all those gauge structure functions and its relation using by using classical master equation or by using field anti-field.
So far we have been doing classical.
Right.
So let's take like quantum error, just the standard Maxwell dynamics.
Yeah.
Just a U engaged field.
Right.
The standard action will probably be fine. I can probably do all of this, introducing anti-fields, etc., etc. Suppose now I take Born-Infeld action.
One?
Born-Infeld.
Born-Infeld. Yeah.
I can still be able to do all these steps, right, from this.
In principle, should be.
Okay, so the fact that it's non-linear it's not going to stop it.
No, even gauge theory, gravity is not non-linear, right?
That's fine, but I wanted to take something that is simple.
Right, you can do it. All known theories can be, if you have a Lagrangian or action.
The action is non-linear, but the gauge transform is linear.
Linear, okay. Yeah, you should be able to do it. So if you have an action in your hand, you can use, you can do it. So that's the theorem. The theorem says that if you are given me an action, classical action, then I can find a proper solution. That gauge. If you have an action, then you can figure out all the gauge transformations. So that's the power of this theorem. So at least you can set up a stage. Now whether you can quantize it or not, that's not guaranteed by any mathematical theorem.
Yeah, Born-Infeld properly quantized it or whatever.
Yeah. So you have to. I mean, I don't know. So there's nothing preventing you to do that, or nothing helping you or nothing guaranteeing you that you can always.
Step should be applicable to one.
Yeah, so far everything should be applicable to any known theory having Lagrangian. So now, once you have master action, I said you can reproduce the gauge algebra and all the gauge structure functions and all the relations. And I'm not going to write down that. That's it's an algebraic exercise that it's just expanding certain fields by taking care of its parity and Gauss number. So I don't want to do that. So summary is that anti-bracket formalism allows a simple determination of all the relevant gauge structure functions that you have in your theory. So remember that in this single step, you are producing all the infinite number of gauge structure functions that you can have. And if you plug in into the classical master equation, it will reproduce or it will produce all the relations that is satisfied by this gauge structure function. So you have the full structure of gauge algebra. So it's a simple trick for getting finding the full gauge structure. And the BV master action, classical master action, is a unique action that you can produce from a classical action of your classical system. I mean, up to some simple transformations. It's a gauge invariance for the classical master action. That's not the gauge transformations.
So I'm just trying to understand. Please show the first step roughly. What do you do? What is it?
Yeah, so here what you do is you assume that you constructed a proper solution. Then take this Ante fields, expand it. So first term is action itself. Second term will reproduce the gauge transformation. Third term will so you have all the structure constants and all the further tensors that you have in your gauge theory or gauge algebra that will be produced here with coefficients as all these Ante fields.
Coefficients being derivatives of delta S.
So you have so the point is that let me write down. If you want, I can just write the structure of it. If you want the structure of it, right? So the second term. So this is again guaranteed. So let's say you have L stage reducible theory. Then the first term is S0. Second term is given by C star alpha S minus 1, alpha S minus 1. This is the ghost field that you had. So this is the Ante field for the ghost field. And then this is the L stage gauge transformation generator. And you have the ghost field for the X stage plus order of C star square.
I'm trying to understand.
So here, so see, this is a gauge transformation that you had.
Is this an ansatz you use? Or
No, this is
this solves that.
this solves that, right?
Solves S.
Yeah, right. So once you have proper solution, you're guaranteed to get this kind of an expansion.
Provided R satisfies the equation they get. Is that right? There's some constraint on R.
No, R itself is a gauge transformation parameter. So you had R phi I given by Ri alpha epsilon alpha. This is a gauge parameter, right? So you had. So this itself is what comes here,
If you didn't know the answer,
right?
you would say S naught phi plus phi star times some phi star A, phi star B times
Something, right? And then that step you don't know what it is, right? Put it back and then see that this term satisfies the gauge algebra.
Where does the gauge thing come from?
It's coming from here. So see, you put it here, then collect all the coefficients for the particular Ante field expansion, so, right? And then set equal to 0, and that will produce your gauge algebra commutation relation. You get the point? So here, so this is all these terms are independent, right? Because so Ante field is an independent thing. Yes. So you take this, you have an expansion, and then put it here, and then set it equal to 0. That means you have to equate term by term this equal to 0. So it's a collection of infinite number of equations. So I'm saying that the first equation is basically the commutator of Ri alpha beta, Ri alpha. commutator of this matrices. And that matrices, it has a structure of an open algebra. So you see that that's a, I mean, in general case. So you put it here, and then that will produce you a commutator equal to R alpha plus a non-shell term. So that's the gauge algebra. So even if you didn't know that that is the gauge transformation, okay, that's fine. So it's just you reproduce.
Exactly the same structure as these are.
Yeah, so the point is that now you don't have to even know that. Initially, how did you derive gauge transformation? You just started with action and then assumed that there is a transformation, and then just found it commutation relation. And the point is that two gauge transformation should again keep the action invariant, right? That was only condition. So what you can do is you just look into the commutation relation, see what you are getting, put it back to your original classical action, then you will see that the classical action is invariant. That means this is a gauge algebra that you have.
On the anti-bracket, you said knows about
Everything. Exactly. So that's why I'm saying this is like the ring in the Lord of the Rings. So this equation knows about the full detailed relations that you have in the gauge theory or the gauge algebra. And that's a surprising thing, right? I mean, it is some simple equation. How do you get it? So that's the structure of gauge theory. So if you have a Lagrangian, BV formalism encodes a full structure of gauge transformations in a single equation. Now once you have all these things, then you can get back your classical BRC transformation.
Is this the way one solve for S5 star? I mean, this way that you just said that you put this expansion back in there and solve it?
Yeah, you have somehow you have to somehow solve the equation. So when you study differential equations, you usually start with an ansatz, right? So you can put an ansatz and then try to see what are the coefficients in your ansatz by putting them back to the equation and solving them, right? So you can.
Algebraic way to solve for.
It's guaranteed that you will get a solution. Then it's up to you. Like you have to just solve it, just like you do in second order differential equation.
But you're supposed to, so you're claiming that once you do this, you get the analog of the gauge fixed.
It is not gauge fixed.
Not long gauge fixed.
It's not gauge fixed because see this has all the antifields, and it has this gauge invariance.
Some intermediate step in it.
Yeah, right. So this is a step where I haven't put any gauge fixing, and without even implementing the gauge fixing, I can start seeing BRC transformation. So this is a master transformation or classical BRC invariance that you have in your theory. I'm going to write down what do you mean by a BRC transformation in BV formalism. So let's start with the field X, and then you want to find a BRC transformation del B, and here I am not going to fix any gauge. Without putting any gauge or without imposing any gauge, I can define an operator del B through anti-bracket. So you have to take X and then compute its anti-bracket with action. So this gives you a BRC transformation, and why I call this as a BRC transformation. So this is the reason is that it's an important operator. This is something which you can derive using BV equation, and then all the physically sensible or physical observable should belongs to the cohomology of this operator del B. So that means a physical observable should be annihilated by this operator del B, and on the top of it, so you say that you have two field configuration or the observables X and Y that are related by a gauge transformation or a BRC transformation from the physics point of view, x and y are exactly equal to the same. So that's why you say that the spectrum of your theory belongs to the cohomology of this operator del B.
But there's no quantization here, it's just classical.
This is just classical. It's just like you do in any simple theories, right? So you just study the classical spectrum. I haven't done any quantization yet. So that's the thing which we are going to do now. So before that, I have to tell you, if I want to quantize the theory, I should be able to write down extensible.
Quantizing it. So how do I read out the degrees of freedom? At what stage will I be able to read out the degrees of freedom?
You mean
Physical degrees.
physical in the sense the true physical degrees of freedoms, or?
See, so far you haven't really, so you have this gauge transformation.
Yeah, true physical degrees of freedom I will give you a quantum analog of what you mean by physical observable. So this is classical.
You won't be able to do it.
At classical level, this is the way you define your observables, right? So all the observables should belong to the cohomology of del B. So and here I haven't done the gauge fixing. I can now, so without doing the gauge fixing, now I can do the gauge fixing to throw away all the Ante fields by introducing a fermionic functional of all the fields, and then assume that all the Ante fields phi star A is said to be equal to del psi.
The details of it.
So this is the gauge fixing. Now once you gauge fix it, you have an analogous BRC transformation. Use that gauge fixed BRC transformation to define what you mean by observable in your theory. What do you mean by physical degrees of freedom?
Size and
It can be any fermionic function satisfying the property that, okay, its status is equal to 1. So given that, you can, any of this psi can be utilized to gauge fix your theory. Now, whether this is an admissible gauge or not, that depends on whether you will be able to expand your theory at a particular vacuum, and then whether you are getting consistent or sensible propagator or not. Some of the gauge fixing may not give you a sensible propagator.
This is like the gauge fixing function in non-linear.
Exactly. So this will throw away all the Ante fields, or basically you should remember that you are not allowed to set all the Ante fields to equal to 0. When you do that, you will just reproduce your classical action, and classical action has all the gauge invariants. So that's not a that's not a good place to start quantizing your theory. So you have to assume something more general. So you introduce a fermionic functional that do the gauge fixing. So this is a gauge fixing fermion, and then implement this condition, and then you are guaranteed that you are throwing away all the Ante fields in a consistent way. And on the top of it, if you want to get a consistent propagator, you have to choose a specific psi. So and choosing what psi depends on your sense. I mean, if you have some intuition, then you can choose a appropriate gauge that simplifies everything. It depends on what you want to prove.
I'm trying to think of some simple but not real example. Because in the standard gauge theory, as soon as I write the theory, I probably know my physical degrees of freedom.
Right.
And then like, okay, if I want, I can kind of go through this, or if I don't want, I can just, I already know it.
Right, you're right.
So what's some simple example where on the face of it, I wouldn't know because of this
complications.
I mean, what is this residual gauge, degrees of freedom, etc.
Right. So in string field theory, I mean, that's the simplest. That's the example that I will anyway discuss. It's not simple, but that's a place where you won't be able to figure out what exactly your degrees of freedom. The only way you can do it, string field theory. No, the point is that that's the example where I don't know how to figure out all these things independently of BV formalism.
Okay, but is there somehow, okay, string field theory, I mean, that is a simple.
Now, I mean, I think that even more simple, if you want, I can give you a lot of examples. Maybe I can discuss next time. I mean, all the simple word line.
I don't know how this thing works, because most of the time, at least in the one that we deal with, as soon as I write S0 of phi, I probably have a pretty good understanding of what the field is.
Right, right.
So if there's an example where at that stage I would not know, But then they're going through this, like, and I'll be able to get more insight.
I mean, even if you, in electrodynamics, also you can do the same kind of stuff,
I already
know it. That's what I'm saying. If you, I mean, in any theory, if I try to tell you, then you know, you will say that you know it. That's why I'm saying I will give you string field theory.
No, okay, you are. There is a simplest context where, like, now you would not be able to. I'm just looking for something simple because.
Okay, I don't have anything in my mind immediately.
Worst and QED.
Right. So this is the way you can gauge fix it, and once you gauge fix it, then you can write down a gauge fixed BRC transformation. That's the usual BRC transformation that you have, and then the cohomology will give you the physical observables. And since the BRC, one can show that BRC transformation or the BRC operator is a graded derivative, given that you can figure out that, or you can you will know that the physical observables or classical observables form an algebra. So so the all operators that belongs to the cohomology of this will give you an algebra. So,
just to understand, when you do this BLST after using the gauge fixing, so you put that after you do this.
I mean, anyway, you can put it. Right. So that's one thing. Like that, this is a generalized notion of BRC transformation. Then you can gauge fix it. Once you gauge fix it, then you can try to write down a path integral, right? Otherwise, it won't make any sense to write down a path integral. So that's the next step. How will you quantize gauge theory using BV formalism? So this is just setting the stage for doing the quantization. So to do the quantization, we have to write down the path integral. So let me denote the gauge fixed path integral by I psi. Say inside the path integral, I introduce a functional or field x. Then the definition is given by the usual path integral definition. So here you are supposed to integrate over all the fields and anti-fields, satisfying the and with the gauge fixing condition delta of phi star a minus del psi del phi a. Then you have action in your exponent. Now here, instead of using psi or the classical master action, you have to introduce a modified master action W. I haven't defined what exactly is W, but I will define. Then you have the insertion, which is the functional of field and anti-field. So this is the definition for your gauge fixed path integral. Now, one should remember that I introduced a gauge fixing fermion here. Now this definition is consistent. So I will explain what is W, but before that, one should remember that I used a particular gauge fixing. Now the final quantization should not depend on what gauge fermion that I use, or gauge fixing fermion that I used. So this object should be invariant when I deform this path integral with a small deformation of the parameter or the gauge fixing fermion psi. So delta that I compute using by deforming the gauge fermion by psi to del psi should not change the path integral. So that is the definition of or that is the way we figure out whether the definition itself is consistent or not, whether it is independent of the gauge fixing procedure that you utilized. So that is the condition. So this condition will impose a particular condition on W and X. And that is the way you will figure out what should be W and what should be the quantum object X that you have to insert, if you want to get a gauge invariant physical answer. So we can.
In the sense that some of the W and X can kind of create something in between them.
Right. So it's basically they have a interrelation, and that's expected. So let's say I start with a situation where X is identity. So I'm going to study the free energy. So I have I psi X, which is d phi, and then only I h bar W phi star. One can find the deformation, and that's not very difficult. And check that the deformation del I psi X equal to d phi. So after I integrate through this delta function, I only have an integration through the fields. Then I have a parameter, I have an insertion, I introduce an operator delta. I will define what exactly that means. And then some object j into delta psi plus terms that are proportional to the a square of deformation. Now, if you want the quantization to be consistent, you demand that delta j should be equal to 0. Now, what is j? J is e raised to iw by h bar. So, and delta is the following operator. It's defined as minus 1 raised to epsilon of so let me just write it as a proportionality. This is equal to delta R, delta phi A, delta R, delta phi A star. It's like a Laplacian. So take this operator and then act on e raised to I delta iw by h. And I have to demand that delta of j should be equal to 0. And one can work out the details and see that this gives you the following equation. Half of Ante bracket of W with W should be equal to I h bar delta W. W on the right. So if the actions or the W satisfies this equation, which is known as quantum BB master equation.
But this could have corrections in h bar square as well.
Right. No. This equation is exact.
But how come you only took the first one?
I mean, all the other things will follow from it. So this itself is a complete equation. See, so you are matching del by c. Del c is an independent variable. So each coefficient should vanish, and it's highly. I mean, if it happens that for this one you get another condition, then that won't make any sense. But I think in principle one can show that if this equation is satisfied, all the remaining thing will follow.
So you see delta j equals 0 is this equation.
This will give you this equation. Now, what you can do is you can write down an expansion for W. So you can propose an expansion in terms of h bar. The first term is say S0, some S0, and then some higher correction h bar P MP, and then put it back to this equation and check that S0 satisfies the BV equation, classical BV master equation. That means W, when h bar equal to 0, becomes the classical BV equation, BV action. Now you have to add further corrections in terms of h bar to make the path integral consistent. So it's more like adding counter terms to the action. So these are the quantum correction to the action that you have. So if you want to define a consistent path integral using a master action, you are not supposed to use a classical master action. You have, at every step, you have to solve the quantum BV equation. So basically, if you solve quantum BV equation satisfying the condition that when h bar going to 0, you reproduce the original classical BV action, then that's a quantum master action which you should use for quantizing your theory.
Confusing because you already completed over phi star.
Right.
Now you have the equation for W on.
So the point is that I have to say that this is on the gauge fixing subspace. So I can introduce a subspace del psi where phi star A equal to del psi del phi A. So all these equations are within this space. So given that, then you have a consistent master action after gauge fixing. And you see that your classical master action gets corrections with coefficients h bar. So this is a quantum BV action.
Now if you do this for QED, this trunking.
Yeah, it depends on. So you can try to write down the solution, and then see that okay, if you don't see any higher counter terms, then everything is fine. Now when you solve it, you have to do appropriate regularization and all, depending on you will get what kind of counter term that you have. So this equation has to be regularized. So this equation itself, this operator itself is singular operator. I don't want to get into those details, but one can show it in explicit examples, and then see that one has to deal this in a careful way. So this is here. The point is that although you have a differential equation, the space of field and anti-field within this subspace, you are not guaranteed to get a solution for it. You don't have any consistent, or you don't have any theorem stating that this equation has a proper solution. Classical master equation has a proper solution that's guaranteed, but here it's not guaranteed that you will be able to solve it. And given that it's actually a victory or big achievement in string theory that you can actually quantize string field theory. Or you can write down the full perturbative solution for this equation. So see, this is an equation that you have to solve. You can decide whether you want to solve it in a perturbative way or an exact way. And in string field theory, you have a perturbative solution for this equation.
What do you mean when you say that you write a consistent path integral in the at that point?
The point is that so I start. So let's say I don't want to do any. I don't care about BV equation, quantum master BV equation. I just use S0 here. Then I can write down a path integral using S here, and then use a gauge fixing procedure. And if I get some number, and then if I change the gauge fixing fermion, I get another number. That doesn't make any sense, right? So you have to make sure that won't happen. I mean, all the deviations can be cancelled by this modification. So if I change gauge fixing fermion with this extra term, I mean, you will get the same answer. So that's one thing. This is a statement about the action itself. Now, what happens to the observable or the field that you have inserted here? So assume that you start with a field x, functional of field and anti-field, and then assume that this satisfies the classical BRC transformation. Or it's invariant under classical BRC transformation. That means it's a consistent gauge invariant classical observable. Now, if you start with such an observable, you have to again ask what happens if I write down this path integral and then vary the gauge fermion. So when I do that, I will again see that there might be a trouble if this x doesn't satisfy following equation.
Just to think of that x as a modified w by w plus how many h power log x, then I cannot get into this equation.
No, actually, I will get another equation. So that equation, like, I mean, the intuition is true. X, compute the anti-bracket of x and w, and that should be equal to I h bar del x. See here, when you assume that h bar goes to 0, the right hand side vanishes. That's equivalent to saying that it's a classical observable. So here.
Should we put both 1 as well as x? So J satisfies del J equals 0 anyway.
Right.
So when you add x,
Yeah, exactly. So if you want to make this expression sensible, you have to write down two equations. First is the BV master equation for the quantum action itself, and then the equation for the x. That means this equation is going to give you a definition for what you mean by a quantum observable. So that's a quantum BRC transformation. Yeah, so you can expand x, and the first term is classical observable x0, and then you have further corrections.
So any solution to that can directly be physical observable or?
Yeah. If you want that x is a physical observable, quantum physical observable, then that should satisfy this equation. So you have to solve this equation and then get what you mean by the correct observable. Yeah. So now let me introduce the quantum observable. So it's the same thing. I'm not going to say anything new, but I'm just going to define the quantum BRST operator del B hat x equal to x minus x anti-bracket with w minus I h bar del x. So again, one can show that this operator is important. Then you can see whether this is a graded derivation or not. So one can see that this is actually not a graded derivation. So if I take a derivative, or a variation of xy, then this is equal to x into variation of y plus a parity factor into del b hat x y minus I h bar epsilon y xy. So this operator del b, the quantum BRST operator, while it's not a graded derivative, and the violation is proportional to h bar, and is given by the anti-bracket between x and y. If the anti-bracket between x and y is non-zero, the del b hat is not a graded derivation. That's equivalent to saying that if you compute all the physical observables and study its algebra, they won't form an algebra. And that's physically, it's equivalent to saying that if you take two observables O1 and O2, classically you can take a product of them. But if you take the quantum, a product of quantum observables or operators, then you will have divergences, and you have to regularize them, and those regularizations usually break the that will break this symmetry. This
Bracket is 0, then it is okay.
it's okay. So if they are spatially separated, they are graded. They form an algebra. Otherwise, not. So that's the thing, and then we can go ahead and then derive all those results that you have in usual gauge theory. So the first thing is that violation of BV master action or BV master equation, quantum BV master equation, is that signals the anomaly in gauge symmetry. So gauge symmetry is anomalous if you see that the BU mass quantum BU mass fraction is not satisfied. And you can study all the global symmetries using BB formalism. And the second thing is that the Schwinger-Dyson equation that you have in gauge theories can be derived using the following statement. So you take a path integral and then replace the observable x with a BRST exact transformation. So it's clear that this should be equal to 0. And as a consequence of this invariance, basically you are looking into the Ward identity for the field and D-field BRST transformation. So that will give you one particular choice of Ward identity is actually the Schwinger-Dyson equation. So, and you can study anomalies and all those stuff using BB formalism. And that means we have a very nice situation. And it seems like we are in a shape that we can study all the quantum effects. But that's not actually true. We are not in heaven. The problem is that, first of all, as I said, it's not guaranteed that we will get a solution for all these two equations. At least for this equation, it's not guaranteed that we will get a solution. And on the top of it, even if he gets a solution, it's not guaranteed that that will lead you to a renormalizable theory. So you can have a non-renormalizable theory which satisfies BB equation or that have a consistent BB quantization, but you may not be able to appropriately regulate or regulate all the divergences. And also,
Regulatory problems don't occur in string theory.
huh?
These regulation problems don't occur in string theory.
I mean, the main there you avoid using some. There is a way to get rid of it. I mean, usual string field theory, you don't have to. Anyway, you don't have a UV divergence, and there's a reason for having that. So that because of the particular interactions that you have.
The modulus with integrations you.
Yeah. So when you have high, so first of all, you start with a Euclidean formulation. In loop momenta, you use the Euclidean loop momenta, and then do a continuation to Lorentz momenta. And then when you do that, you have an appropriate contour prescriptions. So that makes sure that all the at UV, everything is suppressed. It's actually exponentially suppressed. So in string theory, you can. I mean, that's why it's a sensible theory having no UV divergences. But in general, it's not guaranteed that you will get a UV a sensible quantum theory.
So this problem doesn't occur for normal case theories and so on. So this means that
This will occur in. You mean this one?
Yeah.
It occurs in any gauge system.
Any gauge system.
So that's why, I mean, I see you take a OP of two operator, you will get singularities, and then that can be traced to this extra term. When you are looking at classical level, you don't have any trouble, but at quantum level, you are not guaranteed to get an algebra. Maybe in special situations you will get, but I don't know whether you will get an algebra in general. That's one reason why you have difficulty in defining entanglement entropy.
No, but so sorry. If I start with the conformal theory, of course, then you can have this OP of that's how you start with.
So you have all this. So I think it's a modified vertex algebra, right?
Yeah. So you start with an algebra for the operators.
Right, and then the point is that. So even at the classical level, all these algebras, these are sensible algebra. Once you go to the quantum generalization, maybe you have to appropriately modify. You come with a modified definition for your algebra. But it's clear that you will have divergences, right? Depending on when you have collisions of operators, they will introduce a divergence. And if they are spatially separated, then it's fine. Maybe in topological theories, you have most of the time. They have a ring. In general, this is what you see. I mean, here I haven't assumed what kind of gauge theory that I take. Maybe in special situations, since things might be commuting, and then you are safe. but I don't see why should that happen in general. So that's the end of BV formalism. Basically, you can go ahead and then define all the quantum effective action and then follow the BV formalism to get back suggestion equation and all the things that you want. And you can do a lot of things. I don't want to get into those details. So we have enough background for doing string field theory now. So now we will see that there are some simplicities in string theory that makes everything much more simple. So it looks like it's a heavy task to do the quantization of a complicated gauge system. But string theory has its own way to get rid of all the difficulties. So that I will discuss in next lecture.